Okay, I think everybody is there. 1, 2, 3, 4. Only 4 of you. They will wait for maybe 2 more minutes. Let everybody join. We'll start. Okay, I think we can start, people. Hope you're ready. Are you ready? Shall we start? Yes.
Yes, sir.
Yeah. Okay. So we have completed the first law, right? So we saw different kinds of processes: adiabatic, isothermal, reversible expansions, uh, and we did problems on that, right? So that's about one. That's about the first part of this chapter, right? So I told you this chapter can be divided into 3 parts. So first part talks about zeroth law and first law, right? And second part is going to talk about second law of thermodynamics and even third law to a very small extent. And I would say the third part is going to talk about the enthalpy. So I just told you that there's something called as an enthalpy, right? So there are, again, that's the third part and the most important part, I would say, from this chapter, right? So what do you want to see now? You want to see about the second law, right? Or you want to see about enthalpies? The choice is yours. What do you want to learn? Okay, let me tell you
Enthalpy,
what you.
sir.
Sorry,
Enthalpy.
enthalpy. Okay, fine. So we will start with enthalpy then, right? Then we'll finish that. Then we'll go for your entropies, second law of thermodynamics, and all that. Okay, fine. So we'll start with this, right? Okay. So we start with an isobaric process. Okay. So we know what is an isobaric process. What is isobaric process? What is an isobaric process?
So this process takes place at a constant pressure.
Correct.
Like
Right.
change in pressure will be zero.
Sorry.
Change in pressure will be zero.
Change in pressure would be zero. Okay. So the thing is, people, yes, it's going to happen under constant pressure. So we are going to talk about constant external pressure. So see, whenever expansion or compression happens, definitely the pressure of the gas will change. There is no doubt about it, right? But what pressure we are making constant here is about the external pressure. So the pressure which you are going to supply, the top of the piston, right? Whatever the pressure is there it is going to be under constant external pressure. Okay, fine. So if this is going to happen, right? So we'll see what will happen to the first law, right? So I know the equation. I know delta E is equal to Q plus W, right? Okay. Now, since this process is happening under constant pressure, right? So let me put Q as QP, right? What do you mean by QP? QP is heat lost or heat gained at constant pressure, right? As simple as that, right? This is heat at constant pressure, right? Heat lost. I mean, it can be lost or it can be gained, but that is going to happen under constant pressure. Okay. Now, if you can remember how we defined your enthalpy, right? So I'm going to tell that this QP is nothing but delta H, right? Now, how do I define enthalpy now? It's very simple. Enthalpy, delta H, change in enthalpy, obviously, right? So enthalpy is nothing but it is the heat lost or gained at constant pressure. As simple as that. If someone asks you, define enthalpy, right? So you are going to say that in an isobaric process, obviously under that means constant pressure, whatever the heat loss or heat gain is going to happen, that particular Q value is what is my delta H, right? Okay. Now, as you like say, we already have an equation for Q that is NCV del T plus NCP del T, right? Okay, so now this process happens under constant pressure, right? So definitely CV has no role to play, right? So obviously QP will be equal to NCP del T, and that's now we said that is equal to my delta H, right? So just like how we have delta E, that is change in internal energy, right, is equal to NCV del T, right? Just like that, delta H is equal to NCP del T. Okay, so hope like now you can even predict the CP values for all the gases, right? So you know how to predict the CV value for all the gases. For monatomic, it's 1.5 R. For diatomic, it is 2 R. For polyatomic, it is 3 R. All these things we know for CV values, right? Heat capacity at constant volume, right? Now, if I have to find what is the CP value of that particular gas, right? Can you tell me how will I find it from the CV value? Did you understand my question? We know we can predict the CV values depending from what type of gas we have, whether it's polyatomic or diatomic or monatomic, right? So I can predict the CV value. From that, can I predict my CP values also? If yes, how will you do it? Is there any relationship between CP and CV which you can use? Hmm? You can go and put it in the chat box, people, if you don't want to unmute yourself and speak. Okay. I assume that nobody knows, or nobody knows is not possible because I told you nobody remembers is the correct reason, isn't it, people? Right. Okay. So there is something called as Mayer's relationship. I think now this might ring a bell. Yes. Now at least can you tell me what is this Mayer's relationship? I think there's a glare. 1 second, people. Give me a moment. Okay. So yeah, I think now it's fine. Now tell me, what do you think? I mean, you've already seen this Mayer's relationship, MEYER, right? Do you remember what is that? Okay, fine, no problem. So it's a very simple relationship, right? It's CP minus CV is equal to R. Okay, you have to remember this. Okay, CP minus CV is equal to R. So obviously, if you know the CV value, R value is constant. So definitely, I'll be able to find what is my CP value. Is it understood? right? So very simple. You will, like in physics, you will be deriving this relationship, but in chemistry, we don't need the derivation. Okay, and most probably you will not even get questions as such, giving CP values and stuff. Like you'll not be getting it. So, anyways, it's good to know May's relationship is Cp minus Cv is equal to R, right? And I know delta H is equal to NCp delta. That's it. Okay, fine. So this is okay, right? Now we'll try to move on. We'll try to modify this first law. Now we said that if it is going to be an isobaric process, the heat lost or heat gained under this condition is what is my delta H, right? So now how will I be able to rewrite the first law? I will be able to write it like this. How? I have delta E is equal to, now instead of in place of Q, right? I will put delta H because it's happening under constant pressure. So delta H plus W. Very, very simple relationship. Okay. Delta E is equal to delta H plus W. Okay, fine. Now W again I know. Okay, W is basically going to be minus P external del V. Let me put that there. So I have delta E is equal to delta H minus P external del V. No issues. Okay, fine. Now, people, right? So we are talking about change in volume, isn't it? Right? We're talking about change in volume here. Delta V is what we're speaking here, right? Please understand, if I take solids, liquids, and gases, okay, if I take three different phases of a material, or say anything for that matter, solids, liquids, and gases, right? Now, where do you think the change in volume is easier?
Can you repeat, sir?
Yeah, sure. Well, what I'm asking is, if I have solids, liquids, and gases, if I have one solid, one liquid, and one gas, okay. Now, say I give some amount of heat to all of them. I heat all of them. Okay. Now, in which case, obviously, in all the cases, I would say some change in volume might happen. Say, you know that all things will expand on heating. That we know, right? But what I'm asking is that change in volume, what you're saying for all these three, in which of these three you will have the highest change? Hope everybody got my question. Is it that a what is it, a difficult question? Where do you think delta V will be maximum? In case of solids or liquids or gases? Where?
So liquids and solids, I guess. So
Liquids and solids?
maybe like it could be over there.
Maximum.
Yes, sir.
Okay, fine. So I think, is it Rahul?
No, sir, Pranav.
Pranav. Okay. So Pranav is telling that it might be in solids and liquids. So anybody wants to give an objection or say you will agree to whatever he says? Please unmute yourself and tell something. It is just a guess, right? You are already one person gave an answer. So whether you support him or you don't, just tell me that. Or put it in the chat box. We are not moving unless and until you do that. Everybody, I think there are almost like 5-6 people, right? 1, 2, 3, 4, 5, 6. Yeah, 6 people are there. Okay. I'm sorry, I didn't see the chat. Venetia already gave the answer for May's relationship. Okay, yeah. So yes, unmute yourself and tell whether you're going to support. He says that it is going to be in solids and liquids. Is there any other opinion you have? Then you are gonna, okay. So what do you mean by no, sir? Surya, are you supporting him or you have a different answer? Don't make me call names. I can't think any other option. Okay, fine. What about others? Still waiting. Two more chats. Okay, same thing. Okay. I support Pranav's answer. Okay, okay, Rahul. Fine. Okay, right.
Sir,
Fine.
I don't know the answer, sir.
You don't know the answer.
Yeah, sir. I'm not sure about it, sir.
No, anything. What? It's just a guess. If it's a guess, what will be your answer?
Liquid, sir.
Liquids. Okay, fine. So cool. Almost all of you gave the answer, but still there are people who didn't take the effort. But still, okay. So the answer is going to be in gases. It's actually going to be maximum. It's simple, right? Say I have a solid. I try to compress the solid. It's difficult, and liquids are literally incompressible. You cannot compress liquids, right? But if I'm going for gases, it's very easy for me to put a piston and compress it, right? So obviously the change in volume delta V will be maximum for gases, not solids and liquids. Liquids even not even in the picture, right? So because liquids cannot be expanded, it is theoretically you will not be able to do it. Basically, you will not be able to compress a liquid. You will not be able to expand in the sense. Maybe you can
Sir,
boil
but
it.
you told
Yeah.
you will be heating all three states.
Yeah,
Wouldn't
okay,
I
okay.
compress it?
Let me heat it also. Like say I give 10 joules of heat to a solid, to a liquid, to a gas, right? So obviously, where did you see maximum expansion? Definitely in gases only, you will see that there is going to be maximum expansion happening. Now, why is it? Why do you think it's happened like that? Now, I already know, right? So the intermolecular forces, right? The forces which binds solid particles or liquid particles or gaseous particles. In gas, it is going to be minimum. They have very less force of attraction, right? Now, if I'm going to give some energy, right? Obviously, already they have so much kinetic energy. Among three, the maximum kinetic energy will be possessed by gases, right? So if I'm going to give some kinetic energy, they'll move faster. They will try to move away from each other, right? So obviously, gases are the one which will undergo or which will have maximum change in volume. Whether you're going to compress it or are you going to expand it, the delta V will be maximum in the gas, not solids and liquids. Okay, right? Fine. So why did I ask you all this? Is because we are going to derive certain things. Okay. So I see if you see this, this is like say P del V, right? So if I have P into V, I can write P into V as nRT. PV is equal to nRT, right? Now, okay. So now if I have P del V, right? Now how am I going to write this? I'm going to write it like this: P del V is equal to delta Ng RT. So like nRT is there. If I have del V, I just put delta N instead of N, normal N. Okay. So P del V is equal to delta Ng RT. Okay. Now what is this delta Ng? Is the next question. Okay. So it's very simple. I'll tell you. Okay. First, let me substitute it in the equation. Then I'll tell you what is this delta G. Okay. So if I substitute this in this equation, I have delta E is equal to delta H minus delta Ng RT. Okay. Right. Now, what is this delta Ng? Now, very, very simple. Delta Ng is equal to total stoichiometric coefficient of products minus total stoichiometric coefficients of reactants. Oh, wait. Stoichiometric coefficient of gaseous products minus gaseous reactants. Okay, so delta Ng is equal to total stoichiometric coefficients of gaseous products minus total stoichiometric coefficient of gaseous reactants. See, we are specifically mentioning that it is only for gases. Okay, so if I give you a chemical equation, right? If I give you a chemical equation, how will you find delta Ng? We'll see that. Okay, right? Cool. So let me take an equation. Say I have N2 plus 3H2 gives 2 ammonia. All are gases. Okay, N2 plus 3H2 giving 2 ammonia. Right. Okay. Now I have to find delta Ng for this. Okay. Now, how do you find? I told you total stoichiometric coefficient of gaseous product. Okay. Now, if I go to the product, right, I have only one gaseous product. I mean, there's only one product, and that's a gas. And the stoichiometric coefficient of that is 2, isn't it? So I don't have anything else. So I'll just put 2 minus is there, and I have total stoichiometric coefficient of gaseous reactants. Okay, now I have 2 gases here, right? So I have to sum up both the gases stoichiometric coefficient, right? So 2 minus of, now this, for this it is 3, and for this it is 1. So I will have 2 minus 4. So delta Ng for this reaction is minus 2. Everybody got it? Very, very simple. What I did, I just used the formula. Delta Ng is nothing but total stoichiometric coefficient of gaseous reactants minus that of gaseous products minus gaseous reactants. Right. Now in this case, I have only one gas in the product, and the stoichiometric coefficient of that is 2 minus. Okay. Now I have 2 gases are there. For H2, the stoichiometric coefficient is 3. For N2, the stoichiometric coefficient is 1. So I sum it up for the reactants. So you will get the delta Ng value as minus 2. Okay, fine. Another example we'll take. Right. Say I have Fe plus HCl gives me FeCl2 plus H2 gas. This is a solid. This is aqueous solution, and this is again a solid. Okay. So now again, if I want to find delta Ng, can you tell me what will be the value? Wait, I have to balance it. Okay, fine. This I put 2 here. Now it's balanced. Okay. Now tell me, what is the delta Ng for this reaction? Hello. Okay. Let me ask maybe a particular person that might help. Okay. Divya, are you there, Kana? Divya? Divya, are you there? This is not the first time it's happening like this. Why is it happening for Divya always? She's not able to reply. Okay, fine. Some other. Okay. Abhishek, are you there, Kana?
Yes, sir.
Yeah. So can you tell me what will be the delta G and delta Ng for this reaction?
1 second, sir. Sir, delta. Sir, it is -1, sir.
-1. Okay, fine. We'll check. Thank you.
Okay.
Right. Now, people, right? If you say that here I have stoichiometric coefficient of 1, here it is 1, here it is 2, here it is 1, right? So if you are going to say that 1 plus 1 for H2 1, for FeCl2 1, so it is 2, right? Minus, start with products, ending with reactants. Here it is 2 plus 1, 3. So -1 is what we expect. No. Wrong. Why is it wrong? Can someone tell me? This calculation is wrong. Why? Okay. The correct answer for this is delta ng is equal to +1. This is the answer. Can anyone give me an explanation? Why? What did I specify in the formula for delta G? Okay, let me ask again a person. Mithun, are you there, Kana? Mithun? Okay, fine. Pranav?
Yes, sir.
Kana, can you tell me why is this wrong and how this value is +1?
So
Any idea?
absolutely, I don't understand. I'm not sure.
Whatever you feel, whatever, I mean, it might be, it might or might not be correct, but it's okay.
But we can use this for finding delta H. I know only about that stuff, sir, but I don't know why it comes like +1 and all.
Okay, fine. How about Rahul? Do you care to give an explanation? Rahul? Oh, is iPhone 11 yours? I don't know. Some iPhone 11 just told me. Okay. Fine, Rahul. I think fine. So, okay. Fine. Will you give me the? Do you know the answer, Rahul? Why is it like this? Okay, fine. So one last resort, Venisha. I know you can just chat, Venisha. It's okay. Do you know the answer for this question? Why is this is wrong and why is this correct? Ah, do you know the answer, Kana? Venisha? Correct. It's because of solids and aqueous solutions. Very good, Venisha. So the thing is, people, when you looked at the formula for delta Ng, I specified saying that it is the stoichiometric coefficient of gaseous reactants only minus total stoichiometric coefficient of gaseous products first, and here is only gaseous reactants. Now, in this equation, I have only one gas, that is here, H2 in the form of a gas. All the other solid, aqueous solutions, right? So now in the product side, I have one as a stoichiometric coefficient for one of the gases, and nothing else is there. Minus in the reactant side, there are no gases, so 0. So that's how it is +1. Okay, you must consider the stoichiometric, whatever the reaction is. For finding delta Ng, you must consider only gaseous products and gaseous reactants and nothing else. Liquid, solids, aqueous solutions, no. You will not be taking it within the picture. Only gases. Okay, so now everybody understood, right? How is it? I want everybody to just give me an S. You can either in the chat box or you can unmute yourself. Everybody understood?
Yes, sir.
Okay, quickly, everybody.
Yes, sir.
Yes, sir.
Okay, okay, cool. Fine. I'll give you one more example. Let me see if you can answer. What should I do? Any reaction which I have to give? Okay. for this reaction, what will be delta Ng? I didn't specify whether it's solids or liquids, but you should hope you will know what states they will be in.
Sir, is it +2?
Plus,
Sir,
what did
is
you
it
say?
+2?
+2. No, it's not +2. Okay, maybe if I give you the states, CaCO3 I know will be generally in solid state. Calcium oxide will be a salt, will be in aqueous phase, and obviously CO2 will be in gaseous phase. Now, can you tell me what will be the answer?
+1.
Yeah, correct. So it is going to be +1. How stoichiometric coefficient of this is 1. There are no other gases, so 1 minus 0 will be +1. Right? So this is very, very important. Finding delta Ng, you must use only gaseous reactants stoichiometric coefficient and the stoichiometric coefficient of gaseous products. Nothing else. No solid, no liquid, no aqueous solution. Is that okay? Right? Fine. So now we'll go back to your equation. Right? So we have the equation like this: delta E was equal to delta H minus delta NgRT. Okay. So what you understand from this is that the difference between delta E and delta H. So if I take delta H minus delta E, that will basically be equal to delta NgRT. Am I correct? So this will go here, this will come here. Yeah, correct. Right? So the difference between the enthalpy and the change in internal energy, right, will be okay. From this, you can actually understand one more thing, right? So if I consider solids, liquids, and gases, okay, if I consider different phases of any substance, solids, liquids, and gases, right? So what you understand from this is that the difference between delta H and delta E, right? The difference between delta H and delta E is going to be very negligible for solids and liquids. Is it not? Right? Why? Because we're using only gases here. As I told you from the previous discussions, I told you the change in volume, right, is going to be very minimal for solids and liquids, but maximum for gases, right? So the difference between delta H and delta E is not going to be much for a solid and liquid. Whatever the value of delta H a solid has, almost the same value of delta E also the same solid will have. Same goes with the liquid. Say for H2O, liquid, right? For H2O water, if I say that the delta H value is some X, right? So definitely for delta E value will also be X because it's in liquid form. But for gaseous H2O, water vapor, if I take, there will definitely be a considerable significant difference between the delta H value and the delta E value. And that obviously you know how to find. That is equal to delta NgRT. Okay, right? So this is just an introduction for enthalpy. So all these things which you have to know. Okay, right. Now, people, in case of chemical reactions, right? In case of your chemical reactions, which is suited better, right? We can either use delta H or we can use delta E, right? Which will I use is a good question, right? For a chemical process, for a chemical reaction, for that particular chemical reaction, there will be certain value of delta E and delta H. Okay, now which should I take for my calculations? Okay, now I will take only delta H for my calculations because most of the reactions in chemistry are happening under constant pressure conditions. Okay, most of the chemical reactions happen under constant pressure conditions. So that's why we take delta H, and delta E very rarely we take if some case where the process is happening under constant volume. At that time I go for delta E, right? But most of the time, 95% of times, I will go only with my enthalpy and not internal energy for any chemical reaction for that matter. Okay, now depending on what type of chemical reaction I have, right, the names, so I have different types of enthalpy. Say for example, I have something called as enthalpy of formation, enthalpy of combustion, enthalpy of sublimation, enthalpy of neutralization. So I think you understand what I'm trying to say. Depending on the type of reaction, say a formation reaction, CO2 is getting formed, right? So for that particular thing, I'll have a delta H value, right? Say enthalpy of combustion, if I say I have methane, CH4 gas, it is undergoing combustion to form CO2 and H2O, right? Again, that is, I'll have different enthalpy there, right? And say enthalpy of vaporization, if I say what is happening, a liquid is getting converted to gas. So depending on what type of process you do, the name of the enthalpy, as I told you, enthalpy of formation, enthalpy of sublimation, enthalpy of vaporization. So all these things will be different, right? The names will be different, and obviously values will also be different. Okay, and there are going to be so many calculations involved to find the required result. So fine. So for now, you have to know this. Okay, fine. So now we are gonna move into thermochemistry. Okay, so thermochemistry deals with obviously chemical reactions and obviously their enthalpy changes associated with any type of chemical reaction. Okay, so again I repeat, thermochemistry deals with chemical reactions and obviously their enthalpy changes occurring along with the chemical reaction. Okay, fine. Now there are, before we move on to this, right? So there are certain operations which you can know, which will be very, very useful. Okay, say now I have a reaction, say like this, A giving B is the reaction. Okay, right? And say for this, the enthalpy change is delta H, something, some value is given, say 100 joules, 200 kilojoules, something, some delta H is there for this reaction. Okay, now if I reverse the reaction, if I write B giving A, right? If I give B giving A, you have to change the sign of my delta H also, right? So it will become minus delta H. Okay, this is one of the operations which you have to know, right? So for the forward reaction, whatever the enthalpy value you have, for the backward reaction, it will be negative of the forward value. So if here it is some X, here it will be some minus X. Is that okay? Right? This is the first operation. Second operation is, say I have A giving B. Okay, and say for this, isn't it is delta H, right? Now if I multiply the reaction throughout by a factor, say for example, I write it as 2A giving 2B. I have multiplied this reaction by 2. Okay, now obviously you have to make sure that the delta H value is also multiplied by that factor. So for this reaction, the enthalpy value will be 2 into delta H, whatever the, say if it is some X, here it is going to be some 2X. Okay, so whatever you multiply, whatever the factor which with you multiply throughout the reaction, right? So that has to be reflected in the enthalpy value also. Okay, third step, third operation, what you can do is, say for example, I have A giving B, say delta H1, B giving C is delta H2, C giving D is delta H3. 3 different reactions are there. Okay, A giving B, B giving C, and C giving D. Right. Now, from this, if I ask you what will be the enthalpy for this reaction, A giving B. Okay, right? So please understand this. I have A giving B, A, B giving C, and C giving D, and all the enthalpy values are given to you. Right. And in the question, they're asking you, find the overall enthalpy for this reaction, A to D. Now, what will you do? Now, what you understand from this is that if I sum up all the reactions, if I add these reactions, what will happen? A giving B, B plus B giving C, B will get cancelled. Correct? And again, if I add that also, C and C will get cancelled because the reactants and products, or you can plus, minus, whatever it is, right? So what do you see? If I add all these 3 reactions, I will be getting this reaction. Is it not, right? If I add all these 3 reactions, I will be getting this reaction, right? So again, what you do, whatever you did for the reactions, just reflect it in the enthalpy values also. Now you have added all the 3 reactions. So, and I got this reaction. So for this reaction, if I say delta H, that will be equal to delta H1 plus delta H2 plus delta H. Is that okay? Right? So you have ordered all the reactions and the enthalpy values are given. So obviously, whenever you add reactions, add their corresponding enthalpy values also. Okay? So you have to only remember three operations. When I reverse the reaction, the delta H value will become negative of the initial value. Second, if I multiply throughout the reaction by a factor, right? Now that has to be reflected in the enthalpy value also. Say if here for this reaction, if it is X, if I multiply throughout the reaction by 2, the enthalpy value for this reaction will become 2X. Okay, and at last, if you add or subtract two reactions to get the third or fourth reaction, right? Whatever you did, say addition if you did, you have to add the enthalpy values. Subtraction if you did, you have to subtract the enthalpy values for the required equation. Okay, now these three things you have to remember, right? And guys, I think today I'm not feeling that well, right? So we will stop with this for today. Okay, so let me continue this in the next class. Is that okay? Right? So we have almost like 15 more minutes. Okay, so you can go take rest, right? And then get ready for your school, right? Thank you, students. Bye bye. Please,
Thank you,
next class
sir.
when I ask you something, please try to answer at least in the chat box. Okay, fine. Thank you. Bye bye.
Thank you, sir.